myself Sanjana Yadav, and we in a team of 3 are representing complex exponential signal using MATLAB. My teammates are Vaishnavi Kavri and Pratik Kamble. So let us start with what is actually complex exponential signal. Signal whose samples are complex number where the real and imaginary parts of the samples form respectively both the cosine wave and a sine wave.
Complex exponential signal, which is defined at discrete instants of time, is known as discrete time complex exponential sequence. Mathematically, the discrete time complex exponential sequence is defined as S of n is equal to C alpha raised to n, which is also equal to S of n is equal to a raised to n e raised to j omega naught n plus phi, which is also equals to a raised to n cos of omega naught n plus phi plus j a raised to n sine of omega naught n plus phi, where cos part is the real part and sine part is the imaginary part. Depending on the magnitude of A, we obtain different types of discrete time complex exponential signals as for magnitude of A is equal to 1. Both the real and imaginary parts of complex exponential sequence are sinusoidal. For magnitude of A greater than 1, the amplitude of the sinusoidal sequence increases exponentially, and for magnitude of A less than 1, the amplitude of the sinusoidal signal decays exponentially. Like we can see in this figure, R is greater than 0, so the signal is increasing, uh, and here the R is less than 0, so the signal is decaying.
Plot the real part, the imaginary part, and the magnitude and the phase spectrum. So let's take the value of n is equal to minus 20 to plus 20. Our graph will be limited between minus 20 to plus 20 coordinates. Let's take the alpha as minus 0.1 plus 0.3 j. Our exponential signal x of n is equal to exponential of alpha into n. Now we have to plot the real part of the exponential signal. So we will use the MATLAB command stem n comma real part of the exponential signal. X label will be the time samples and Y label will be the real part. Now we have to plot the imaginary part of the exponential signal. So we will subplot it at 4, 1, 2 as the second graph, and we will use the MATLAB built-in command stem as n comma imaginary of the exponential signal. X label we will give as the time samples and Y label will be the imaginary part. Now we have to plot the magnitude spectrum, so we will use the subplot 4, 1, 3 as the third graph, and we will use the command stem as n comma absolute part of the exponential signal, that is ABS of exponential signal, and X label will be the time samples and Y label will be the magnitude. So now the last one is the angle, that is the phase part of the exponential signal. So we will subplot the fourth graph, that is 4, 1, 4, and we will use the command stem n comma angle of exponential signal, and X label will be the time samples and Y label will be the phase of the signals. Now let's run this code in the MATLAB. So this is our MATLAB code we have written in the MATLAB, online MATLAB. Now let's run and see the output of the signal. Here we can see the 4 graphs. First one is the real, second one is the imaginary part, third one is the magnitude, and fourth one is the phase. So real part, as our a is less than 1, so our graph will be the exponential decaying cosinusoidal signal, and imaginary part will be the exponential decaying sinusoidal signal. Yes.
Real-time applications of complex exponential signal. The complex exponential signal do not really exist, they are just a mathematical representation. Technically, it frequently comes when we deal a signal in frequency domain. For example, sinusoidal signal can be represented by algebraic sum of two complex exponential signal, and we do this factorization because it is easy to handle these complex signals mathematically. That is, doing Fourier transform of complex signal is very easy.